Let's consider an example as this. How do we get this into the graph? You will notice that we have three constraints here, or somebody will say two constraints, but sometimes I add the non-negative constraint, sometimes I don't add it in saying the number of constraints. So look out for that. Whether I mention it or not, you should note that it's part of the constraints. All of that variables should be greater than or equal to 0. So now let's look at how do we solve this problem. Okay. We will need to draw the graph on a graph sheet. Okay, so we have two equations. Now we are converting 2x plus 2y plus to 5 because we're going to draw the line. But of course, we know the less than will come afterwards. We know which side will be less than, which side will be greater than. Then we shape that appropriately. Then the second one, 2x plus y equals to 4. So let's name this equation 1, this equation 2. I want to solve this simultaneously. And why am I solving this simultaneously? I would want to find out the solution. This is not drawn to graph, so I won't get the correct answer, but I can draw it not to scale and solve the two equations simultaneously to get a solution that I can draw and it will be accurate on the graph. All right, so for now, let's draw the graph. Our interest should be how do we get the line down? Let's get the coordinates. For the first one, for the first equation, let x equals to 0. So if x is equal to 0, our y, 2y is equals to 5. So just divide by 2, divide by 2, and our y is equals to 5 over 2. The next one is if x is equal to 0, we have this. So the first coordinate is 0, 3, sorry, 5 over. Let's y on the same equation, let y equals to 0, and we have 2x to 5, 5. So divide this by 2, divide this by 2, x equals to 5 over 2. Coordinates will be 5 over 2, 1. So we have that coordinate already. So 5 divided by 2 would be 2.5. Let's get a second one. On question 2, let's x equals to 0, so that we have y equals to 4. And if and our coordinate there will be 0, 4. Again, on the second equation, that's y equals 0, then 2x equals 4 by 2, divide by 2, and our x equals to 2. So our coordinates in that 2 is 0 and 2. So we have 4 coordinates now, 2 per each equation. Let's scale our graph here. Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4. Again, it's not drawn to scale, so let's see how we can get this done without drawing it to scale. So the first coordinate is 2, 0, 5 divided by 2, and 5 over 2 is 2.5. So we are going to be here. Our 0, 5 divided by 2, and then our 5 divided by 2, the second coordinate, is right in the middle here. So what we need to do is now draw a straight line. So we draw a straight line that will pass through these 2 points using the ruler. So like this. Okay. And then we can call this one 2x plus 2y equals to 5. The next line, that is the second equation, we have the first coordinate that's 0, 4. So we have 0, this is where our 4 is, and then 2, this is where 2 is, 0. So again, we are going to rule that line to pass through them. Forgive my lines there. Then name this one 2x plus y equals to 4. Now we have these two graphs perfectly labeled here. Let's go back to the first graph. Let's take 2 points, one here and one here. Okay, So 1 here would be maybe 2 and then 1, or 2, let me put 1 and 1 that I know is inside. So if I put 1 1 inside the first graph, which is 1 2 1, this equals to 5. No, this is equals to 4, and 4 is less than 5. So that inequality part is satisfied. So it means that I actually have this, I can see it here. Anything that is below here satisfies that particular what constraint, the equation or inequality. The second one is the same way. If I should take the points to the left and the points to the right, the points to the left will satisfy that equation. So I'm going to give one a different color. Okay, so let's redraw this line, and then we take is also less than or equals to. So you would realize that there is something here. This had drawn it to scale. We will have this here being some little triangle there, which will not satisfy the two of them. It will only satisfy this one, it will not satisfy. So we can say that is part of the feasible region. Now the other two constraints that we have at the bottom, our x and y, they also count, because if you look at what I have drawn, I have gone past here. This is 0, 0. So it means that if y is greater than 0, anything from here going to my right, all these are positive values. All these are positive values, and that satisfies the y constraint. Again, the x2, anything that is here and up positive. Okay, now the question is, looking at the graphs that I have drawn and the directions of the inequalities, which place will satisfy all four equations of all four inequalities? Remember, this one is standing alone and that is standing alone. And because they are sharing the same right hand side value, we decide to just put them like that. So the four inequalities, they all agree on a particular location, and that is the location we call the feasible region. So let's shade that, and this is the feasible region right here. Okay, so this nice area is our feasible region. Now, what next do we want to do? We want to get the solution, and now our solution will now depend on the different combination x y, the different combinations. If we put that into the objective function, which of them will give us the maximum value? Because here we are maximizing. All right, so let's do it again. And then come here. This right here is our corner point, the intersection between the two lines. Then here is another corner point. We are not taking this because it doesn't satisfy all the conditions, so we cannot include that. Of course, this is another point, this is 0 point, and this is another one. So this one we know it to be 0, 4. This we know it to be 0, 0. This one here we know it to be 0 and 2. What we don't know is this guy here, and that is the one I said we could estimate it if we want to, without actually drawing it to scale. So let's clean here a little and then do our little magic to get it done. Okay, so how do we solve that? We solve it simultaneously. If you look at the two equations that we have, I can use the elimination method. And what is the elimination method? Subtract one equation from the other. Okay, so let's say if I want to subtract 2 from 1, so equation 1 minus equation 2 will mean that 2x minus 2x will be 0. 2y minus 2y will be y equals to 5 divided, 5 minus 4 will give me 1. So already I have one solution. The next one is I choose any of them to solve my problem. So let me go with equation 2. 2x plus y, which is 1, equals to 4. So I'm going to have 2x, which equals to 4, 1. So x equals to 3 divided by 2 1.5. So our intersection here is actually 1, comma 1. So this is our corner point at the intersection. Let's get this down. We are going to need them, so let me write them clearly at the top here so we can go to the next slide. Use them. 0, 0, 4, um, 2, 0. Actually, here is 2 and 0, not the other way around. Then we have 1 and 1. So these are the four corner points that we are going to look at and see which of them actually will give us a maximum profit. Again, I'm going to take this off to give room for some other calculations. So I'm going to draw a table like this and put our point there, here, and put our z. Z is equals to the objective there, 3x plus 2y. And the first point is 0, second is 1, 0, 5. These are the points I'm going to be looking at whilst considering the objective equation. Put 0, 0 there, everything is 0 here. If x is equals to 0, then 2 multiplied by 4 will give us 8. If y is equals to 0, then 3 multiplied by 2 will give us 6. Here comes the last one. So 1.5 multiplied, that is 3 over 2, multiplied by 3 plus 2 multiplied by 1. So we are going to have 9 divided by 2 is 2. Find your LCM here. So divide here by 1 over 2 here. So we have 9, 4, which will give us 13 over 2. So here will be over 2. So that will give us approximately 0.5. So this is equals to, okay. So which of them will give us the maximum? The maximum will come from here. So use 4 of the y's and don't consider the x, and you will get a maximum profit of 8. This is how we solve using the graphical method.